Hello, everyone, and welcome to today's webinar, Proper Controls for the Bigfoot Spectral Cytometer. Beads are not cells, but are they close? I'm Susie Valdez of LabRoots, and I will be your moderator for today's event. Today's educational web seminar is presented by LabRoots and brought to you by Thermo Fisher Scientific. To learn more, visit them at thermofisher.com. Now, we encourage you to participate today by submitting any questions you might have during the presentation. To do so, simply type them into the Ask a Question box and click Send. We'll answer as many questions as we have time for at the end of the presentation. You may also submit any technical issues here as well if you have any trouble seeing or hearing this presentation. This webinar is educational and thus offers free continuing education credits. Please click on the continuing education window at the bottom of your screen to obtain those credits. I'd now like to welcome our speaker, David Adams, Managing Director at University of Michigan Biomedical Research Core Facilities in Flow Cytometry Core. David, welcome. You may now begin your presentation, sir.
Well, thank you. Good morning, everyone. As she said, my name is Dave Adams, and I've been running the University of Michigan Flow Core for the last 20 years. More importantly, I like to start each and every talk with a blatant typo to set the audience at ease. So for those of you wondering about Bigfoot Spectral Cytometry, you're welcome. Now, Thermo Fisher is hosting this webinar, and the Bigfoot is a remarkable sorter. But I'm going to try and keep my comments more system agnostic. Each system excels in certain areas. The Bigfoot with its simplified workflow, the Aurora with its exceptional ability to handle universal negatives, the ID 7000 with its frustrating tendency to be something I haven't bought yet. But in the end, the approach to its controls is similar across all systems. Next slide button is there. The struggle to have users prepare proper controls is certainly nothing new. I asked a few core directors about their biggest pet peeves when it comes to users and compensation controls, and the responses were all eerily similar, and very much the same as my own. I'm sure if you take a glance at some of these, you're all going to recognize some issues that you've had to deal with. And with Spectral, these things really only become more challenging. Of course, this challenge is, at least to some extent, a self-inflicted wound. In many cases, our enthusiasm for the new technology caused us to pass along vendor claims, and as a result, to set our user expectations way too high. We've all heard, and many of us have repeated the idea that with Spectral, you will no longer have to do compensation. That is, of course, blatantly untrue. Sure, we're no longer telling the instrument to take X% out of detector A and subtract it from detector B, but we're still compensating for spectral overlap. It's simply that by looking at the fingerprint of each fluorochrome over a wide spectrum of both excitation and emission, we're no longer looking to adjust the signal by a wee skosh, and are performing the spectral deconvolution in an information-rich manner, pulling specific threads from the cellular tapestry rather than scooping out roughly the right amount of mint chocolate chip from each signal. So, if we are still, quote unquote, compensating, what is the difference in the necessary controls between the conventional compensation approach and spectral unmixing? Well, honestly, when you get down to it, there is no difference. In fact, you know, the dirty little secret of spectral cytometry is that the algorithm is actually even more dependent on the same rules we've had along. The algorithm requires proper controls and allows for no shortcuts. I was speaking with Rachel Sheridan from the Van Andels, and I really think she put it best when she said, and I'm paraphrasing here a bit, I like the spectral workflow because it calls shenanigans on sloppy work much sooner than conventional. So, if that's all true, what are the proper compensation controls? If you do a quick Google search, you'll see spread across umpteen sites these three simple rules of compensation that we just keep repeating. This is the University of Iowa's version, and they're mostly true. Going in reverse order, you have to have the same fluorochrome for comp controls as used in this example. Simple enough. APC shouldn't be used to comp for our Lexiflor 647. With our gray matter, historically, our wetware algorithms, we've been able to make that adjustment for the user. But in Spectral, it's not an option. The curve for APC is going to be very different from a Lexiflor 647, and you won't be able to make that adjustment. Second, background fluorescence should be the same for the positive and the negative. Certainly this makes sense. When we're running beads, we need to have a negative bead sample to adjust against. When we're running cells, we need to have that unstained cellular sample present to compensate again. And I actually have started asking, not only with beads, I've asked my users to start spiking in unstained cells with their single positive controls, because again, as I mentioned earlier, not all systems deal as well with the idea of a universal negative, and making sure that we have unstained cells in every single positive control allows us to be sure that we're going to get a good, clean spectral unmixing every time. Finally, we come to this idea that the controls need to be bright or is brighter than any sample, any signal in the experimental sample. Pardon me. In Spectral, this technically is no longer true. Regardless of intensity, the curve for a given fluorochrome is going to look the same wherever it falls on scale, assuming that it is, in fact, contained within the scale. However, I generally will intentionally fail to mention this to my users, because if they've made a mistake in some other part of their control, then I know by having that brightest sample is the single positive control sample, I'm still set up for success should I have to revert from Spectral to a conventional compensation procedure. Now, these rules are great. Like I said, we see them all over the internet throughout course because they're accurate, they served us well. But when training our users for Spectral, we really need to be more specific in what we're telling them. As such, we need to expand our list from the three simple rules to something a bit more elaborate. And first, we have to be absolutely certain that users understand that the negative controls and the viability controls must be cells. This is necessary to account for autofluorescence and the inability of spectral workflow to account for fake viability markers. In my conversations with other core directors, I had one individual state that their users insist on bringing beads with ECD on them to act as a viability control for the PI state. Again, our wetware matrix can make those adjustments. We can make that system work, but the spectral algorithm simply will not allow this unmixing to proceed because the curves are different. Control samples should be treated identically to the stain samples. Now, I found my own users failing to follow this rule. Actually, I had a vendor's tech specialist point out that some of my users weren't following this rule, which is infinitely worse. But controls and experimental samples need to be treated the same way. The buffers used matter. The washes matter. Fixation status matters. These all affect the nature of the final products. Shortcuts here can scuttle your experiment. One of Spectral's early promises was the idea that a reference library could be created so that under appropriate circumstances, and I'm going to highlight that phrase, under appropriate circumstances, the library could be used instead of preparing single positive controls. Now, this is actually a practice I actively discourage in my lab, as I want my users to prepare complete experiments each time. Call me superstitious. But it is important that users understand that this library concept does not apply to tandem dyes. Tandems age, they leak, they dissociate over time. Pi7 is the poster child of bad tandem behavior, and users need to know that these curves can and they will change with each use. And I hit the next slide and did not move to the next slide. Please hold. Technical difficulty. Conjugates used for the control and experimental samples really need to be from the same lot and company. While the fluorochromes produced by Acme and those produced by Aperture Science are all going to be detected through the same bandpass filters on our instruments, that doesn't mean that the spectral curves are going to be identical. Age and manufacturing process affect the final product. But so far, all of these rules have been fairly easy to follow. Good practices will yield good results. But what about situations where things aren't so simple? What about situations where they've got a dim marker and you can't fully resolve it from the negative control? Well, even with the spectral algorithm, you've got to assign positivity and negativity. And with a dim marker, it's hard to do. It makes for a poor comp control. Rare populations make for poor comp controls. If the population is sufficiently rare, you may never get enough events for a positive peak that the algorithm can act on. And if they're using fluorescent proteins, even though we have asked our users time and time again to make sure that these proteins don't fall into single positive controls for other colors, invariably we end up seeing them. So what do we do in this situation? Where do we go? Well, we need another solution. And that solution is compensation beads. Now, I promise to be agnostic, but I am going to state that UltraComp and UltraComp Plus beads are simply the best beads for the job. They are more compatible over a wider range of experimental workflows than their competitors. The author would like to state that he is in no way acting as a paid sponsor, but UltraComp beads for the win. So, using compensation beads is a simple enough procedure, but the same care has to be utilized when prepping bead samples as cellular samples. And there is an excellent resource out there currently available for everyone to read. It's free access, and it's in the September issue of Current Protocols. And in fact, I'm going to be stealing heavily from the article in the next few slides. If you take a look at the authors listed on the article, I'm sure you will be able to recognize the expertise that's present. Grab that article, read that article, go into your lab and frame that article. Everything in there is so very important to optimizing that spectral experiment. So it's free access, so make copies, pass it around to all your users. It's long because it covers a lot of different what ifs, but it is well worth your time. So assessment of your experiment starts with determining where things are appropriate to use. Cellular controls here, bead controls there. And they have described, and a lot of us have come to the realization on our own, that the easiest way to determine whether beads make for a successful control set is to actually throw them on the cytometer and find out. And in order to do this, you really have to, again, set yourself up for success. So the first step is always going to be to titrate your antibodies. This step, for whatever reason, is one of the first to be skipped by users in their experimental designs. And yet it's clearly the most critical in order to ensure that you have enough stain to properly resolve a population, and yet not so much stain as to obscure the signal with induced noise. So the users have to titrate their reagents every time. They shouldn't use shortcuts like just looking for the brightest staining point. They need to take the time to consider the actual staining index, brightness, and the spread of noise. Most third-party software will calculate these automatically for the users, so there's really no excuse for sloppy technique. And as the person in charge of flow, in charge of the core, in charge of the stray instrument in your lab, you really have to stand firm on this. Titrate your antibodies. Then the next step then will be for users to stain their beads. And at this point, I really want to call you back to a previous slide. Control samples should be treated identically. This includes beads. If you're staining your samples one way, you absolutely have to stain your beads the same way. They have to be washed, just like the cells. The buffers matter. Make sure that the cellular workflow mirrors the bead workflow, and you'll reduce problems experienced by the user. So how do we proceed next? Easy enough. You've got your experiment prepared. You run your negative and viability controls, and then for every other control, you use beads. Once the bead controls are run, you do an unmixing. Then you take another set of controls prepared with cells all the way across the board, and you run those cellular controls as unmixed samples. And at this point, although the matrix can get really large, if you're running a 20-color sample, you need to look at every color combination and determine if the mixing produced no errors, as in the first sample on the left, or if in fact the spectral unmixing is suboptimal, as in the sample on the right. And if the sample is not appropriate, or the beads are not appropriate, you're not getting an appropriate mixing, then you need to consider something else for controls. Now that something else may be committing even more of that. Excuse me, for some reason my Alexa has started going off. That's something you generally don't get in my office. I apologize. So as I was saying, at that point where you can see with the beads you're getting an insufficient spectral unmixing, you either commit more of your precious sample for controls, or you need to identify a surrogate tissue. That tissue may be another mouse sample with similar protein chemistry, a similar cell line, what have you. But in this case, you're still going to have to go through the procedure, titrating. You've done the titration, so you then need to go through the control samples again, now using the surrogate tissue, unmix, and then again, look at your samples. Have they unmixed properly? Have they not unmixed properly? I do have a tendency to charge through when I'm talking. So this 30-minute presentation has somehow ended up being a 20-minute presentation. I apologize for that. But I do want to thank you for taking the time to consider ways your users can optimize their experiment. And I want to give special thanks to the people at Thermo Fisher who got me set up with my 2 Bigfoots in a timely manner. And then special thanks goes out to Rachel Sheraton from the Van Andel and Jessica Back from the Caramanos, who I routinely use to bounce thoughts and ideas off. And extra special thanks goes out to my own flow cytometry team here at the university, who, as you can plainly see, we have never taken a group picture together. So you can always reach out to me at the university if you have any questions, but because of my tendency to talk very, very fast, we do have time to actually have a discussion. So if anyone out there has questions, wants to call me out for something I said that they believe is wrong, now would be a good time to have that discussion.
Well, thank you, Dave, for that wonderful, informative presentation. And we will, in fact, start the live Q&A portion of this webinar. If you have any questions you want to ask Dave, please do so now. Just click on that Ask a Question box located on the far left of your screen, and we'll answer as many questions as we have time for. So let's take a look. We already have some great questions from our audience members coming in. Dave, you failed to mention FMO controls. Can you share your thoughts on those?
I absolutely can. You are correct. I did not mention FMOs. I consider, in my own mind, FMOs fall into a different category. They're not really involved in that spectral unmixing or the conventional compensation workflow. They're actually an experimental control that comes after that. And if there's any doubt, even though the spectral workflow produces, if done properly, a superior unmixing, that still doesn't remove the spectral background that's created by having 10, 15, 20, 25, 30 different fluorochromes emitting off these cells. The background is there's always going to be a higher spectral background on your fully stained sample than there is on the unstained cells. And as such, I consider FMOs to be critical, absolutely critical to the workflow as your experiments become more and more information and data rich.
Thank you so much. Our next audience member asks, what do you suggest in situations where beads are not appropriate, but no surrogate tissue is available? How would you proceed?
Well, as I said, you can always commit more of the original sample, but there's a lot of situations where there's just not a lot of original sample. We do a lot of work with Drosophila brains and that sort of thing, and there's just not much there. So you can't really commit that extra sample. So you can get close with your bead controls, and it's at that point where if you don't have a surrogate tissue you can use, the beads just aren't quite there, it's time to take a step back, take a deep breath, and remember that the machine doesn't need spectral unmixing to function. We, the user, need spectral unmixing in order to be able to draw those populations. So it's time to sit down and really evaluate your data. And at this point, it's important to understand the biology, what it is. You go into these experiments, you need to have some idea of what you expect to see. So you can, even if the unmixing isn't absolutely correct, you can take a look and see if the populations you expect to see are still there. And if you can isolate them to get phenotypic information, if you can draw gates to sort the populations out, maybe you're okay. If If not, if things still look a little cramped, you can fall back on your grayware algorithm. There's nothing preventing you from taking an unmixed sample and tweaking compensation in a conventional manner. However, if you make those choices, you need to disclose that information to anybody you present the data to. And it behooves you to verify that the decisions you're making are appropriate. And these days, with the availability of the technology, sequencing is a wonderful way to say, you know, I had to tweak the optics a bit. I believe that I have identified or segregated this population. Well, we're going to take one of these flies and we're going to pass it on to sequencing and make sure that what we're saying is the population is actually the population that we're giving people.
Thank you so much, Dave. And again, I want to thank our audience for these great questions coming in. Our next question, when you're titrating your antibodies, what PMT voltage do you use? And do you change this protocol for spectral versus conventional flow experiments?
Well, that's a dangerous question, especially in the conventional end of things. There's always the argument new flow versus old flow. In the conventional workflow where old flow, you're setting your negative population in that first decade. New flow where you're doing voltrations on your instruments and setting those voltages to the optimum signal to noise ratio. On the spectral side, the machines try and take care of that for you. On the Bigfoot, you throw on your negative sample and you tell the machine what percent of scale do I want my negatives falling in. It's a bit of a reflection of old flow there, but it does make sure you have a nice even base to start your curves. On the Aurora side of things, on the other hand, they have their QC process with their Cytec assay setting, where they're always trying to start the machine again at that best signal to noise ratio point, and you proceed from there. Now, where on both of these machines that can be a challenge is if you put on your controls and you find that something's falling off scale. How do you adjust for that? Well, on the Bigfoot, you might go back to your negative control and say you set the baseline at 25%. Maybe you set it for 20% to make sure that the positives are captured on scale, but also just as importantly that your negatives aren't falling off scale. On the Aurora side with their Cytec settings, it's important because everything you do on that machine relates back to the curves generated during those Cytec assay settings. It's important that you, first, you're adjusting lasers, not individual detectors. And if you lower or raise the laser power on one line, that you proportionally adjust all the other lines to make sure that the curves are still proportional to what was developed in the Cytec assay settings. And again, you need to ensure that if you're lowering laser power to make sure that something stays on scale, you need to check and make sure that your negatives are not being forced off scale.
Thank you so much, Dave. Now, are there ever cases where you need to change your compensation controls when transitioning a regular flow panel to a spectral flow cytometer?
Part of the message, I hope, of this whole talk was if you've done the job properly conventionally, then you don't have to change anything for a spectral workflow. If all of your controls follow all of the rules, you're good to go. But again, there are situations where people have been relying on wetware assumptions. I'll refer you back to that ECD for PI. And dim populations that a machine algorithm isn't going to, you're not going to be able to separate negative from positive. That again, with our brains, we're able to make assumptions. We've seen it 1,000 times before. We know how to tweak things. But in an ideal situation, your compensation controls, if they're prepared properly for conventional, they're going to be prepared properly for spectral.
Thank you so much. Now, can you still do manual compensation with spectral flow cytometry?
Well, as I mentioned, in situations where the beads don't work 100%, you don't have the surrogate tissue that's appropriate. Sometimes you have to tweak it a little bit using more conventional compensation. But again, if you do so, it's incumbent on you to not only disclose that information, but to prove to the user, prove to anyone they're presenting to, that those assumptions resulted in the tissue that you say you're giving. The analysis you say you're giving is correct. And like I said, there are ways to do that, sequencing and whatnot. But once you add conventional to spectral, the burden is on you to prove that that's an acceptable choice.
Dave, I want to thank you for your presentation. Would you like to provide any closing remarks to our audience before we go?
I like cheese. Sorry, private jokes. About 3 people in the audience got that. The rules haven't changed. It's just with the spectral, we need to enforce the rules. And people have over decades developed shortcuts, especially if they're running the same procedure all the time. They try and operate in automatic mode, and any shortcut you take is going to cost you in spectral. So in theory, it's a simplified workflow, but to get that simplified workflow, you have to be very precise in the preparation before coming to the machine. And just if you try and cut a corner, you're going to cut the validity of your experiment. Now, if like I said, if you have any other questions that occur to you later or want to chastise me for speaking so fast, here's my contact information. I love it when people reach out and we can have a discussion. So make it so.
Dave, I want to thank you again for your time and for your presentation. And I also want to thank LabRoots and our sponsor, Thermo Fisher Scientific, for underwriting today's educational webcast. And before we go, I also want to thank our audience for joining us today and for their interesting questions. Questions we did not have time for today, and those submitted during the on-demand period will be addressed by our speaker via the contact information you provided at the time of registration. And this webcast can be viewed on demand. LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. Until next time, take care, everyone. Stay safe. Bye-bye.